Hello and welcome to Lecture 5 of Energy in Phys 1101. And in this lecture we're returning to the topic of collisions, which we last looked at when we were studying momentum, because energy can also be useful in analyzing collisions. So remember that whether we're dealing with an accident investigation, with a car crash, or perhaps dealing with the path of a spacecraft where we know where it's going before it interacts with a planet and we want to know after, or if we're trying to work out something to do with rocket propulsion where the rocket is pushing gases out the back and we want to know what the forces are on the rocket, we can use momentum. And this was last unit, and we used this fact that momentum is conserved in a collision if the system is isolated. And this is true if the system is isolated, if there are no external forces, and we can often make a good approximation that this is true if a collision takes place quickly. And this lets us solve for velocities. This is sort of the point. We know some velocities, we want to know some others. Conservation of momentum gives us a way of doing that. So now we're on to energy. Can we use conservation of energy in a similar way? So I want to stress again that momentum and energy are two very different things, but we're going to work by analogy. Conservation of momentum, when we have a collision between two objects, looks like this equation, right? That's a sum of the initial momentums and it equals the sum of the final momentums. So can we do the same thing perhaps with kinetic energy? Because kinetic energy also depends on the masses and velocities. So maybe we could write down an equation that looks like this. And this looks kind of like conservation of kinetic energy, right? This is the total kinetic energy before, this is the total kinetic energy after. But there's a problem. There's no such thing as a law of conservation of kinetic energy. There is a law of conservation of energy, but energy isn't quite like momentum. Momentum is momentum is momentum. All momentum is momentum. But there are several types of energy, and so kinetic energy can turn into other kinds. Remember that kinetic energy and other types of mechanical energy interchange, transform into each other easily, and they can also turn into thermal energy, although then they don't tend to turn back. So if we're going to use this, we have to worry about this fact that kinetic energy tends to transform into other types of energy. Those transformations into thermal energy are going to turn out to be one of the big problems we need to deal with. Remember that friction tends to turn mechanical energy into thermal energy. There are lots of other situations where mechanical energy gets converted into thermal energy. For example, when you hammer a nail, just before impact, the hammer is moving rather quickly, and so it has a lot of kinetic energy. But after the hammer hits the nail, it's essentially at rest. The nail will have been driven a short distance down into the wood, so it will have moved briefly, but it's been brought to rest. And so all the mechanical energy in the system has disappeared. Now you may have experienced that if you hammer a nail, the nail warms up. In fact, if you hammer a large nail, you can often heat it up enough that if you accidentally touch it, you'll burn your fingers. So there's a lot of friction going on as the nail is driven down into the wood, but also the impacts of the hammer with the head of the nail, which is a normal force, produces thermal energy as well. But the other thing that's happening is that as the wood is being split open, as the nail is driven down into it, there are a lot of molecular bonds being broken, and that takes energy too. There's some terminology that we use when we're talking about collisions, and it's related to terminology that we use for talking about other things. When we talk about an object being elastic, we mean that it's springy. It tends to return to its original shape. Things like rubber balls, springs, elastic bands, those are all elastic. Whereas an inelastic object is deformable and tends to stay deformed when you change its shape. Things like clay, bread dough, wax, those are all inelastic. So when you go to the swimming pool and use the diving board, you expect that it will spring back. You store some spring potential energy in it when you try to dive off, and it returns that energy to you. On the other hand, if you go to a pool where the cheapskate owner got a great deal on a wax diving board, that's not going to work so well. So let's apply those ideas to collisions. When the objects in a collision spring back, in other words, they're elastically colliding with each other, then the kinetic energy before the collision gets temporarily stored as spring potential energy during the deformation of the objects. But after the collision, it all gets returned to kinetic energy. And so we can ignore the middle, right? Because the energy 1 equals the energy 2 equals the energy 3, and we basically have a law of conservation of kinetic energy when this happens. On the other hand, if the objects that are colliding remain deformed after the collision, then at least some of the kinetic energy that the system had before the collision gets transformed into thermal energy. And now the kinetic energy after the collision is different from the kinetic energy before. And so we would then call this an inelastic collision. I often find that students get confused about all the types of collisions, and admittedly there's a lot of terminology here. All we mean by elastic is that the kinetic energy before the collision is the same as the kinetic energy after, or in other words, the mechanical energy was conserved. And just because objects bounce off of each other doesn't mean the collision is elastic, but the objects do always bounce off each other in any elastic collision. Objects are not deformed after the collision if it's elastic. That's the real way to know whether a collision is elastic or not. And generally, this is only true as an approximation. We'll often say that a collision is fairly elastic if the kinetic energy before and after are close, and perfectly elastic if they're exactly the same. And you usually only see perfectly elastic collisions between, say, atoms or nuclei. On the other hand, an inelastic collision is any collision where the kinetic energy before is not equal to the kinetic energy after. The mechanical energy is not conserved, but it could increase or decrease. We usually pay more attention to the cases where it decreases, but there are certainly cases where the kinetic energy increases. In an inelastic collision, the objects may bounce off of each other, but then again, they may not. But in any case, the objects are deformed. There are more types of inelastic collisions than elastic collisions, so let's look at a few of the special cases. If we just say that a collision is inelastic, we often just mean that this is some collision where the objects rebound more slowly than they would in a similar elastic collision. But if they actually stick together, that's called a completely inelastic collision, or a totally inelastic collision, or a perfectly inelastic collision. Many students get mixed up and think that's the way you tell whether a collision is inelastic, and that anytime a collision is inelastic, the objects stick together. But that's not true. That's a special case of inelastic collisions. On the other hand, you can have what's called an explosion, where the objects start out stuck together but then go flying apart somehow. This is sort of like the opposite of a completely inelastic collision. Well, here the kinetic energy is increasing, so it's inelastic. And so this is a case where you get a kinetic energy after that's greater than the kinetic energy before. So suppose the momentum and mechanical energy in a collision are both conserved. So this is a perfectly elastic and also isolated collision. That means you have these two equations, conservation of momentum, conservation of kinetic energy. And this can be very convenient because now that you have two equations, you can solve that, even if you only know 2 out of the 4 velocities. So this is one of the reasons we study perfectly elastic collisions, because they're convenient. If this is a one-dimensional case where the two objects are in line with each other so that we don't have to worry about the vector nature of any of this, then solving this is fairly easy. Now I'll say, solving this pair of equations can be quite a mess and is pretty intimidating to students at this level. And I don't really care in this course whether you're able to solve this. Just realize that in this special case, where object 2 is at rest, you get this nice solution. And this can be useful. Now, I'll stress, as usual, I do not want you to memorize these equations. I don't see what use it could be to you in your future lives to memorize these, and so I won't make you. But realize that they exist and realize what special case they apply to. So back in lecture 4 of the unit of momentum, we were looking at this car crash in a parking lot. So we had one parked car, stationary, being hit by another, and tire track lengths and so on told us what their velocities were immediately after the collision, and we wanted to know how fast this car was going before the collision, and we used conservation of momentum to find it. We found that it was going 11.5 meters per second. Let's just look at the energies. So the kinetic energy before is just the kinetic energy of car A before. And so that's just a half ma va squared. Okay, so a half 1,200 kilograms times 11.5 meters per second squared. And if you plug that into a calculator, you're going to find that that is about 7.94 times 10 to the 4 joules. Now, on the other hand, if you look at the kinetic energy after, that's going to be a half ma va prime squared plus a half mb vb prime squared. So that's a half. I'll just factor out that half, and I've got 1,200 kilograms times 4 meters per second squared plus the 1,500, right? 1,500 kilograms times 6 meters per second squared. And plugging that into a calculator, you get 3.66 times 10 to the 4 joules. So notice that those are very definitely not equal. The energy of the system has been about cut in half during this collision. And notice that these did not stick together. So this is not completely inelastic or totally inelastic, but this is an inelastic collision. So let's now compare that with a perfectly elastic case. Let's suppose we had a perfectly elastic collision between these two cars. Now this is actually ridiculous. Looking at cars after car crashes, you see they get very, very deformed. Car crashes are not even close to elastic. But, you know, maybe these cars are made of adamantium or some other comic book material like that. And so in this case, we have the two objects colliding and the one stationary, and so we can use these equations that we just got. So VA prime is going to be MA minus MB over the sum of the masses times VA. And you can go ahead and plug in those numbers, right? 1,200 kilograms, 500 kilograms, and the initial velocity of 11.5 meters per second. And you'll find that VA rebounds back the direction it was coming at about 1.3 meters per second. Whereas VB prime now comes out to 2MA over MA plus MB VA, and again plugging in all those same numbers, you get about 10.2 meters per second. And if you compare that with the inelastic case, in the inelastic case, relative to each other, these cars are going almost the same velocity afterwards, whereas in the perfectly elastic case, they wind up recoiling from each other at quite high speed after the collision.